here is a very, very clever application of Green's theorem. You can actually use Green's theorem to compute area. So usually when we have Green's theorem, let me kind of quickly write up Green's theorem. The integral of f dot dr is equal to the double integral over r partial n minus partial x minus partial m partial y dA here. Usually the kind of questions that I ask you is like verify both sides, or we use it to, I ask you about this, and instead of computing this, you compute this. So usually we use it going in this direction. You know, we usually say that this is going to be the easier direction to compute. But sometimes we use it going in the opposite direction to compute area. Okay, now think about for a second, we want to compute area. How do we compute area in general? The area of a region R is given by integral of 1 over that region. And so how to make this an area calculation? Well, if the partial derivative n with respect to x minus the partial derivative n with respect to y is equal to 1, then sure enough, we do end up with the integral of the area. So the question then is, well, what vector fields f have the partial derivative n with respect to x minus partial derivative n with respect to y equal to 1? So here's 1. So f is the vector field 0, x. So it's the partial derivative n with respect to x, that's 1, minus the partial derivative m with respect to y, that's 0. 1 minus 0 gives us 1. Another possibility is g is negative y comma 0. Partial derivative n with respect to x here is 0, minus the partial derivative m with respect to y, minus negative 1. This also gives us 1. And one more, negative y over 2 comma x over 2. And so the partial derivatives are 1/2 minus negative 1/2. That gives you 1 as well. And so if you use any one of these three vector fields here as your f, if you evaluate the integral around the boundary of one of these three vector fields, you'll get the area. So for example, the integral over c of 0, x dot dr, which we can rewrite as the integral over c of x dy, is equal to integral of 1 dA is equal to the area of R. And so this is very, very cool. This allows us to compute the area of the region just by doing a vector line integral around the boundary of the region. Let's put this to use. Let's just do a very simple, the simplest possible warm-up example. Let's compute the area of a circle of radius r with Green's theorem. So we need a parametrization, r cosine t, r sine t. And this will give us, let's see, the derivative here will be negative r sine t and r cosine t. And so f of r of t, I guess we have to say which one of these choices are we using? I'm just going to pick this as our f. So f of r of t ends up as 0, replace x with r cosine t. F of r of t dot product r prime of t. This dot this is 0 plus r squared cosine squared t. And so the area is going to equal the integral from 0 to 2 pi, those are our bounds on t, of r squared cosine squared t dt, and I'll let you check for yourself. I'll let you check for yourself that sure enough, you do get pi r squared. So here's the factor r squared, the rest of this gives you pi, so pi r squared. As desired, as expected. So this is a kind of toy example. But let me wrap up this video just by kind of saying, like there are real life examples of this. And actually one of them comes from my dad's line of work. So in my dad's line of work, there are these meters that are counting things, and they get read over. They are recording things over the course of like a month. And so what happens? Let me not use that marker here. Is that you get a picture that looks something like this over the course of a month. And the idea here is that as time kind of ticks from the start of the month to the end of the month, you go around here, and basically things are more or less being recorded in polar coordinates. So the angle is telling you what day you're on, or what more specifically what time of the day you're on, and then the distance there, the distance that you are, is telling you how much stuff is going through the meter at any given point in time. And so the thing that we'd like to do then is to count how much stuff went through the meter over the overall course of the month. And so that's just asking for, that's a really bad line there, but this is essentially just asking us for the area of this region. And so, area, we could do this in polar coordinates if we had an equation for the curve here. If we had an equation for the curve here, then we could use formulas, but this is something that, we don't have an equation for this, of course. This is something that is, real life data is messy, right? This is something that was churned out somehow by, written down on some graph. And so it turns out, how do we do this? Instead of calculating area inside of here, that we end up, when I say we, the guy in my dad's work whose job is to read this kind of stuff, calculates the area by doing this kind of calculation. And of course, he's not doing it by hand, but there is some kind of a little device. There is some kind of little device that basically is doing this kind of calculation, that it is, you basically trace it over all of the boundary of your region here, and somehow it's able to mechanically compute, as you're tracing it over the boundary of the region, it's able to keep track of the like the distance you are away from things and change and stuff like that. It's probably using the H form, I would bet. But somehow it's able to physically compute this vector line integral, and by this equation right here, you get an area. And so there is a very, very nice application to this. That's, as I said, is at some point I was just talking to my dad about things, and somehow we just, he described this as like, I know exactly where that comes from.